Okay, I think we'll go ahead and get started. Um, I'd like to welcome everyone to the second entry in our seminar series for the AERA SIG on systematic review and meta-analysis. My name is James Pustiewski. I'm the SIG chair, and today I'm very pleased to welcome Dr. Brenton Wiernik as our feature speaker. Dr. Wiernik is an assistant professor of organizational psychology at the University of South Florida. He also holds a PhD in IO psychology from University of Minnesota. Brenton is both an applied IO psychologist as well as a methodologist in the lineage of Hunter and Schmidt. He's also an open source software developer. Among other projects, he maintains the Psych Meta package for R. He also contributes to several other open source projects, including Zotero, which is every research synthesist's favorite reference management tool. Today, he's going to be sharing some of his methodological work on psychometric meta-analysis. And so without further ado, please join me in welcoming Dr. Brenton Wernick. Oh, before I pass it over, I forgot to mention, Brenton's indicated that he's happy to take questions during the presentation. So feel free to put questions in the chat as he is sharing his work. And then there will be a discussion and Q&A period at the end, during which you can either put questions in the chat or use the raise hand feature on Zoom, and we'll call on you to for verbal questions. So please take it away.
Thanks so much, James, and thank you everyone for coming today. I'm really glad to be here and share some of my thoughts and perspectives on how we can think critically about our data and what we're putting into our meta-analyses, and try to think about, well, what are the potential biases or sources of misestimation that are coming from these studies, and how can we leverage some various approaches to statistically adjusting for those to try to give us a clearer picture as to what might be going on with our phenomena. Just excuse me. I'm sure she will be back many times during this presentation. All right. As an introduction and as a kind of beginning, much of the content that I'm going to be talking about today, we've written about in this paper here, published in the journal Advances in Methods and Practices of Psychological Science. Here we provide a kind of broad overview to approaches to correcting for measurement error or selection biases in meta-analyses, including kind of collating and curating a variety of different formulas and estimators that have appeared in kind of disparate forms all over the place. And so this is a place where I'm not sure I've ever seen someone lay down adjusting for different types of group misclassification in the context of meta-analysis. And so we try to be rather comprehensive in the various types of artifacts and potential corrections that might be applied for them. And that's available from SciArchive here, as well as published in AMPS. So to start off, let's ask just kind of broadly, what is the purpose of meta-analysis? What are we trying to accomplish when we do a systematic review, evidence synthesis, and then ultimately do estimate a statistical meta-analysis model? And one kind of widespread perspective, in the way that we often talk about it when we are teaching or introducing the concept of meta-analysis to an audience, is to say, well, here, our purpose is to summarize or critique a body of studies, to say, here's what is consistent about the results in these studies, here's what's inconsistent, here are moderating factors that seem to be associated with effects of larger or smaller sizes, as well as then to critique those studies and identify potential risks of bias in those, things like potential for publication bias or weaknesses in the experimental design, lack of control groups, lack of randomization, poor quality measurement. And so one approach or one kind of perspective is to say, well, meta-analysis is a tool for understanding and taking stock of the literature and indicating what is the kind of consistent and reliable message that might be extracted from that literature. And this is a perspective that I think is, fairly widespread and really kind of seems to stem from the lineage of meta-analysis from Gene Glass in education, and Rosnow and Rosenthal, and other early advances and developments of meta-analysis from the education and policy and medical literatures. An alternative perspective that I think is also useful to think about is that meta-analysis can be a tool to enhance those studies, to understand and facilitate, what is the best possible inference that we can extract and draw from a set of data about their research questions. So what are the potential sources of bias in the individual study results, and how can we leverage all of the information that's available in a literature to be able to best estimate, what is the answer to these research questions? If we're trying to estimate a causal effect, what is our best estimate of that causal effect? We're trying to estimate the predictive power or utility of a particular indicator for some outcome or criterion of interest. How can we best estimate the operational validity, the operational utility of those predictors for the populations we're trying to understand? And this sort of perspective of meta-analysis as tool for understanding sources of bias and adjusting for them, this is a perspective that kind of comes out of the Hunter and Schmidt lineage, and especially the industrial and organizational psychology lineage of meta-analysis. And it's one that I think we, initially in kind of the history of meta-analysis did not get a lot of traction and did not get a lot of attention and buy-in from a lot of different folks in various meta-analysis communities. But I think that as we've seen meta-analysis evolve and develop as a tool for research and for evidence synthesis, I think that there's a lot of recent innovations in things like risk of bias assessment, in network meta-analysis, in model-based meta-analysis, where we can see really strong parallels with some of the ideas and philosophical approaches to meta-analysis that we saw initially emerge in psychometric meta-analysis, focused on assessing biases in studies and trying to make our best guess as to how the results may have been impacted by those biasing factors. So let's think about a couple of major types of factors that bias study results that we might be able to address and examine using statistical corrections. So the most prominent one that we focus much of our attention on in meta-analysis is sampling error. And this potentially creates a lot of artificial variability and inconsistency, non-systematic heterogeneity across our results. And it was this heterogeneity due to sampling error that was in many ways the impetus for the development of meta-analysis in the first place, to try to rein in narrative reviews and say, hey, what is actually really inconsistent versus what is just reflecting sources of random noise. We might also think, well, various studies that we've estimated, they're plagued by confounding. There's unmeasured confounding variables that are giving us biased estimates of any particular effect size in our individual studies. We might also look at our effect sizes, our results, and seeing, well, there's really, there's low quality measurement. There's lots of measurement error. There's contamination of our measures by other factors that are not relevant to our variables or our constructs of interest. And also we might be concerned that our samples that are contributing to these results are quite biased. So we might see that we have a very restricted range of a particular variable in our sample, and that's attenuating the possible effects that might be observed. We might also be concerned that due to some sort of selection process, an important outcome of one of our variables is being restricted, and so that's producing collider bias, where we're inducing and creating spurious relationships that might not otherwise be there if we were to examine the effects in our broader population of interest. And these are the types of things we've increasingly seen being raised and brought up in discussions of research integrity, of research reliability. Much of the issues that we see being discussed in the context of the various crises in social sciences, generalizability, replication, we've seen discussion about confounding and bias sampling and collider bias kind of show up all over the place in terms of how people are looking at individual studies and critiquing and evaluating them, and then trying to design their studies to provide better estimates of the true underlying causal effects. And because there's all of this attention that's being given to these sorts of issues in primary studies, I think it's worthwhile to revisit some of the approaches that have been developed and applied fairly widely in meta-analysis within some disciplines to try to address these, not at the level of individual studies alone, but also at a broader level in terms of how can we understand the contours and parameters of literature when we're subjecting it to meta-analysis. So as we're examining and looking at studies, we might ask, in addition to what is the risk of publication bias, what is the risk of bias due to things like omitted confounding variables or poor experimental control, we might also ask things like, hey, how might the effects we're observing in this meta-analysis, how may they be biased by poor measurement? Or how might bias sampling or selection bias have impacted the effects that we're observing? Might they be attenuated relative to the broader population that we're interested in making inferences about? Might the signs even be reversed if there's some adverse selection or selection on outcomes? And can we pull information from other samples to remove confounding? Can we estimate the relationships of confounding factors with some of our focal variables by drawing on samples from other settings? And those are all questions and approaches that we can leverage meta-analysis and meta-analytic methods to address. In addition to qualitative or conceptual review of studies in our assessment of risk of bias, we can leverage statistical estimation of those effects. And this approach, this idea to meta-analysis as a lens for understanding bias in studies, this is a really long history. In the very first meta-analysis that Hunter and Schmidt published in 1977, they adjusted for sampling error in their estimate of the heterogeneity of effects across studies. But they also estimated and adjusted for potential biasing effects of low quality measurement and measurement error, as well as variability in the range or the variance of the various variables across their samples. And they found that if we they argue that there are plausible measurement models and plausible selection bias models that are acting on the various samples they included in their meta-analysis, and that not only contributed to increased variability in the results across studies, but also had a substantial effect on the mean effects. And they argued that attention to that bias can help us to make clearer and more accurate estimates of the relationships between the core variables themselves, if we could, versus the imperfectly designed and constrained studies that were on the ground. And now initially, as I kind of read the meta-analysis literature, and especially the methodological literature as it's grown over the last several decades, there's always been kind of this sense that the Hunter-Schmidt corrections, as they're often referred, have been held at arm's length, and we're not sure exactly what is being argued or why those might be applied, and there's been a fair amount of skepticism applied to them. And I think that that's a little unfortunate, because those approaches to statistical correction for artifacts like measurement error and selection bias, they have a lot of parallels and a lot of connections to other practices that are really common in systematic reviews and meta-analysis. And I think that there's a lot of value in attending to what are those links and how can we leverage statistical corrections to help us do things that we already are doing in systematic reviews and during the meta-analysis process. So one of those, the big one I would say is risk of bias assessment. As even over the course of my career as a meta-analytic methodologist over the last 15 years, I have seen the methods and approaches for risk of bias assessment just really kind of explode in terms of their quality and the attention that's being given to those. Especially in psychology, it was not unusual even 10 years ago to see very little attention being given to risk of bias assessment during a meta-analysis and systematic review process. And I think that as a field, psychology still has a long way to go in terms of meeting some of the standards and quality of those assessments that are more common in say the policy and medical literatures. But I still seeing pretty massive improvement in terms of actually thinking critically about what are the studies going into this meta-analysis and what are their implications for the ensuing results from the meta-analysis. And many of the factors, sources of bias that are considered during risk of bias assessments that appear on all sorts of different checklists and tools for doing this process include things like lack of control groups or randomization, or lack of control for important confounding factors, or poor quality measurement, or restricted sampling. And most of those sources that are commonly cited as representing a high risk of bias or potentially high risk of bias in the studies contributing to a meta-analysis, many of those have estimable and reliable effects on results. And we can potentially apply statistical adjustments to quantify how large might those effects of something like poor quality measurement or restricted sampling, how might those have actually impacted our results, rather than kind of leaving it at, well, these results are likely to have been substantially affected by a particular source of bias. We can try to estimate, well, how large might that be? How consequential might this bias really be if we were to make some assumptions about the measurement process or the selection process? Similarly, we can see that there's increasingly attention across a wide variety of social and biomedical sciences to enhancing the methods and approaches to doing causal inference and causal modeling. And we see that methods such as estimating causal structural models, or using directed acyclic graphs or generative models to model what is the actual flow of causation between our variables, has started to become much more widely adopted across all sorts of different fields. And we're seeing especially really common practices that have been well established for a long time in fields like epidemiology and econometrics are starting to make their way into fields such as psychology and sociology and epidemiology to help guide our questioning and approaches to model building and identifying what are important covariates or confounding factors that should be included, or how might different parts of the sampling process, how might those be inducing some spurious correlations or biasing in the causal relationships amongst our observed variables. And one thing that we'll look at here in this presentation is to see that there's really deep connections between pieces of these causal models, things like collider bias, selecting on the common outcome of some variables, and the types of corrections we do, things like for applying corrections for measurement error, or applying corrections for selection effects and range restriction. And there's also interesting connections between statistical adjustment for artifacts and model-based meta-analysis. So in the vein of Betz-Jane-Becker or meta-analytic structural equation modeling by Mike Chung and colleagues, where these are approaches to estimating meta-analysis models that are aimed to estimate full structural models, including relationships amongst multiple variables, rather than merely single parameters. And these types of models are often used to test particular causal sequences, or perhaps to adjust for confounding, or to include measurement models that can estimate relationships while accounting for measurement error. And these types of approaches to incorporating and estimating meta-analyses for broader systems of variables, as opposed to focusing on single bivariate relationships, these are also becoming kind of much more common in the broader meta-analysis literature. And we can see that there are strong links of these types of approaches and statistical adjustment for things like measurement error or selection bias within a single study. And it's just saying, where are we drawing that information from? Are we drawing that information through the meta-analytic modeling process, or are we estimating the consequences and effects of measurement error within a single study and incorporating that into the way that we estimate the effect sizes for that study? And so altogether, I think that there's a lot of opportunity to look at how might we use study-based estimates of things like reliability and measurement error, or potential magnitudes of selection biases, and how can we incorporate those into the meta-analysis models that we estimate. So today I'm going to talk about two major classes of statistical artifacts that we can estimate the effects for in individual studies and incorporate corrections or adjustments for those effects into our meta-analysis estimation. So first we're going to talk about measurement error, and then we'll talk about selection biases. So measurement error is an artifact that causes the observed or measured values for whatever variable we're estimating to deviate from their true values, in some way. And these deviations might be overestimates, or they might be underestimates, and these affect every measurement individually. And so one person in a sample might have their score overestimated, another person might have their score underestimated. And across different fields where these where measurement error is considered and discussed, it's variously called measurement error, or unreliability, or observational error, or information bias, or low precision, or misclassification. And some examples of this might include, random fluctuations in scale responses. So perhaps I might choose a 4 on a 5-point scale instead of a 3, or I might not be paying very close attention to some of these scale items, and so I respond in a somewhat random or unpredictable way to some of the options. In a treatment setting or an intervention setting, measurement error might be induced or created by treatment noncompliance. So we expect, and we're operating as though a person is in the active group, but in fact they aren't really paying, following the treatment protocol very closely, and so they're more similar to a member of the control group than to a member of the treatment group. When we're collecting data using ratings of some sort, there might be idiosyncrasies of each rater, so that one rater might use the response scale or interpret different stimuli or events one way, and another rater might respond in a different way. And we might generally not regard those idiosyncrasies or differences as particularly meaningful, and in fact, we want to average over those and see what is the more consistent or systematic effects of our stimuli or items on rater responses. Similarly, we might measure variables using one instrument in one study or another instrument in another study, and we might want to know, well, what is the consequences of the specific content, the specific form and structure of the instrument that we're using across different studies in our variables. And so broadly, we can think and group measurement error into 4 broad categories or sources of measurement bias. One might be random response error. So this is error that is specific to each item or response. So it's unique to each measurement. So this might be things, if we're looking at a rating scale, people being momentarily distracted, or randomly choosing one scale point versus another for a way that's not systematic or tied to any particular identifiable reason. Secondly, we might look at transient error. This is error that's due to the specific environment or period in which we're gathering data. So this would be things like rater mood, or the particular semester or time window in which we're collecting the data. And perhaps for example, if we were to collect information all during March 2020, that might look a lot different than if we're collecting it 2 months earlier. And so some of those random fluctuations or impacts of the environment, they affect all the measures that are gathered at the same time, but they're not going to be shared and consistent across measures that are separated in time or space. We might also look at the specific content that's on a particular instrument. That's called content sampling error or instrument error, as well as then the rater or the source from which we're collecting this data. And if we used a different instrument, or we collected using different raters, we might get different responses. And all these different 4 major categories of measurement error, they induce some additional variability or unsystematic and variance that we don't necessarily regard as being particularly relevant for the actual variables that we're trying to study, the phenomena we're trying to study. We can describe and divide measurement errors into both systematic and random components. And systematic error or bias, affects every score in the same manner. So for example, there might be consistent underestimates. So for example, let's say that we were looking at the effect of exposure to particular environmental experiences on learning outcomes. We might consistently underestimate or miss people who are exposed to those experiences. So that affects the kind of mean across people and has a rather consistent effect overall on our relationships. The other type of measurement error is random measurement error, which affects each score differently. And that primarily impacts the variance of scores across people. And typically, if we're going to look at standardized effect sizes like correlation coefficients or standardized mean differences, these are primarily only affected by the random measurement error, where they're increasing and artificially inflating the variance of scores. Though if there's differential bias across groups or score ranges, that could also potentially impact their means. For any individual single measurement, we don't know the direction or size of the measurement error. If I administer a measure to one person, we might overestimate their score for all the various sources of measurement error. If I administer it to the next person, I might underestimate their score. Someone who's filling out a depression survey, who's had a variety of recent tragic life events, might, due to transient error, inflate or get a higher score than we would typically expect for that person. Whereas someone who's had a lot of positive events in their life might rate themselves on a lower score. And so the direction and size of these fluctuations is kind of unknowable across people. But once we have many measurements, we can potentially ask and quantify, well, how much do these various sources of measurement error, how much do those affect the variability in our scores? Are our scores kind of twice as variable or 10% more variable than they otherwise would be if we could measure our variables in a way that is absent those sorts of random biasing factors? We can conduct reliability studies to estimate the magnitude of that error variance. So how consistent are measures across time or raters or across items in a scale? And so let's say, for example, that I want to estimate the relationship between relatively stable home factors in terms of the different features in a student's environment and their school learning outcomes. We might be concerned that, to some degree, some of these stable home factors in terms of rating about resources or experiences or events that occur in the home, those might be kind of variable and fluctuate over time. And so if we wanted to estimate, what is the overall kind of aggregate effect of these factors, we might want to, average over, some weekly or monthly fluctuations in some of these experiences. So to quantify the measurement error in that home environment measure, we might administer it multiple times. We might administer it, at one period, and then say a month later, administer the same measure and see how consistent are those scores. Or are they quite variable or inconsistent over a fairly short measurement period? If we assume that what we're interested in is kind of the consistent features of these measures that are stable and affecting the person, consistently and regularly over time, and if we assume that those, random fluctuations, the reasons that they're differing from week to week or month to month are independent of kind of their stable basal level, and the other measurement errors or fluctuations, we can quantify how much might the variability in our observed measures be affected by these measurement errors using what's called a reliability coefficient. And so that's the correlation between those measures at multiple time points. And we might design other types of reliability studies to estimate the consequence or impact of other sources of measurement error, like the particular instrument we used, or the raters that we've used, or other features of our measurement process. And the reliability coefficient, that's a ratio of our true or stable variance from the total variance. And so he's saying the proportion of the variability that we're seeing across in scores across people, how much of that is consistent or stable versus how much of that is potentially varying across instruments or time periods, whatever sources of error that we're estimating in our reliability study. And when we have a lot of measurement error in our studies, the typical effect that we observe is that by inflating the measurement error, we attenuate effect sizes. So for example, if we, in our panel A here, and we look and see that the correlation between our two variables is 0.5, and they each have a standard deviations of around 0.9. If we then add some measurement error and reduce the reliability of these measures from 1.0, perfect measurement, to 0.80, so we inject 20% noise, random noise, into our measures, we attenuate the correlation between these two variables down to only 0.4. So we've reduced its magnitude by 0.80, by 20%, and we've inflated the standard deviation of our two scores by a 10% increase. And so a typical effect that we'll observe when measurement error is operating in this random fluctuating manner is that we're going to obscure effects, make them harder to observe, and also reduce their magnitude. And so for estimating, what is the predictive utility of a particular factor, or what is the causal effect of a particular factor in the study, we'll tend to underestimate it to the degree that we have this random measurement error operating. And we can see similar patterns when we look at other types of comparisons. So for example, if we have misclassification, we might, where we are operating as though someone is in one group, whereas they are effectively operating in another group. So for example, if they're not complying with treatment protocols, or if they are engaging in the treatment but mislabeled as being in the control group. For example, perhaps they're engaging in some alternative treatment on their own outside of the auspices of the control process. Then as an estimate of the treatment effect as implemented, the observed treatment effect as assigned is going to potentially substantially misestimate our target effect. So here, for example, if we have a standardized mean difference of 1.0 with no misclassification, but then we misclassify 20% of our group members so that some people who are labeled as being in the control group are actually functionally in the treatment group, and vice versa, we attenuated our observed standardized mean difference by 30%. So dropping it from 1.0 down to 0.70. And generally the effect or the measurement error is going to have three major effects on the results of meta-analysis. So one, typically it will have a systematic null bias on the mean effect size. So for example, if we look at our observed correlation compared to what the true measurement error-free correlation would be estimated to be, it'll generally be attenuated by the square root of the reliability coefficients for our two variables. And so for measuring our variables, with reliabilities around 0.8 or 0.9, we might attenuate a correlation from 0.32 down to only 0.24. And the more severe our measurement error, or the lower our reliability is, the more severe this attenuation is. Second, measurement error can also inflate the heterogeneity, our estimate of the variability of our effects, our random effects across studies. And so be particularly severe if those measurement errors are correlated with some moderator. So for example, let's say I'm comparing the effectiveness of cognitive behavioral therapy and a mindfulness therapy for treatment of post-traumatic stress disorder. If the treatments are really equally effective, but the CBT studies measure their variables more reliably than do the mindfulness studies, then we might artificially create the appearance of a moderation effect. And really, we can attribute the differences in those results to these differences in measurement quality. And so if we want to say, what is the effectiveness of these two treatments, we really need to consider, well, are they really comparable in terms of things like their measurement quality? Or are we going to be misled and conclude that there's a difference in effectiveness just due to differences in a statistical artifact that has some fairly reliable general tendencies in its impact on study results. Similarly, the measurement error can also confound or create problems when we're looking at things like estimating the potential for publication bias. So for example, one thing we often see is that depending on how difficult and expensive different types of studies are, they vary in terms of the quality of their measurement. So for example, if we're looking at educational or social science studies that work on relatively small samples, often in those samples, there's a lot of attention to giving quite robust and rigorous measurement of constructs. So the scales are often include many items. They tend to work with instruments that have had a lot of validation work and tend to be quite reliable long measures. In contrast, in large panel studies like the PISA or other large studies that include really big samples of hundreds of thousands of people, because these are very big, very expensive studies, there's a push to economize and kind of make use of every item as much as possible. And so often the measures of the constructs that are included in those large studies tend to be much weaker. They tend to have relatively few items, and they tend to have more measurement error compared to longer studies. So for example, if someone were to include a measure of personal values in the World Value Survey, that tends to include scales where different types of values or dimensions of values are measured with one or two items. Whereas in smaller studies, they'll tend to be measured with scales that include 10 or 20 items for that dimension. So in that context, if we were just simply to examine, what is the relationship of this measure with some outcome, and not attend to, well, what is the difference in the quality of the measurement, we might see a funnel plot that looks something like this, where we see a clear difference in the size of effects across larger studies and smaller studies, where smaller studies appear to have substantially larger effect sizes compared to our larger panel studies. However, the only reason that effect is happening there is because there's better quality measurement in the smaller studies. In the larger studies, they have more error-prone measures, which will tend to attenuate and reduce the size of potential effects. If we correct for that, and so we can examine the construct level, or kind of try to estimate, if we could remove the measurement error, what might those effect sizes look like, then we can see that that difference between our large and small studies here will disappear entirely. So measurement error can create spurious appearance and moderator effects or publication bias if it's correlated with other variables or other features like moderators or sample size in our studies. But we can potentially correct for these for measurement error. So for example, if I'm going to use the correlation coefficient or a standardized mean difference as my effect size, I can estimate what is the size of a measurement error-free effect size by dividing by the square root of the reliability coefficients of our measures. We're going to apply that both to the effect size itself, as well as to the standard error. And those adjusted effect sizes and adjusted standard errors, those are what are going to be used as input into our meta-analysis when we're estimating our various meta-analysis models using whatever statistical model you want to apply for your meta-analysis. For groupness classification, rather than using the square root of the reliability, we'll tend to use a correlation between someone's assigned group or labeled group as well as their true group. And we might, for example, do a sensitivity study to try to estimate what are the rates of misclassification or what are the rates of treatment compliance. Or for some sort of intervention study or manipulation study, we might look at, for example, what is the correlation between group membership and scores on a manipulation check or a treatment compliance measure. So in our when we're correcting for measurement error in our meta-analysis, we can take one of two approaches to trying to quantify and adjust for its effects. One might be that we could correct for the effect sizes individually. So we can go through each study, estimate what the reliability is in that study, and apply those corrections. And we can use those adjusted effect sizes and standard errors as the input for our meta-analysis. And if there's missing reliability coefficients, we can impute it. For example, we might, do a meta-analysis of reliability coefficients and fit a meta-regression model to be able to estimate what is the reliability of variables in a particular study based on its features. And we can then use that as input for our reliability corrections in those studies. Another approach that we can use is called the artifact distribution method, where we take a meta-analysis model that's fitted on observed effect sizes, and we apply post hoc corrections to those parameters, the means, the meta-regression slopes, the heterogeneity estimates, based on what the anticipated effects of the measurement error would be across studies in aggregate. So for example, we can take our estimate of the mean effect size and correct it using the mean of the artifact estimates to give us an estimate of the overall effect on the meta-analysis results as a whole. And we can similarly correct our heterogeneity estimates by subtracting the estimated amount of effect size variability that was due to artifacts. And formulas for quantifying this variance due to artifacts under different sorts of correction models are described in detail in our AMPS paper. And I think that measurement error as a particular artifact is a really important and useful thing to think about in the context of meta-analysis, to think about how much and in what way might measurement error have been affected or adversely impacting the results of a meta-analysis. And if we can reasonably estimate the reliability of our measurements and our assumptions that the measurement errors are uncorrelated with the true results, if those are reasonable assumptions, we can use corrections in this way as an important sensitivity analysis to say, here's the results that we observe based on the statistics reported in studies, and here's our estimates of how they might be affected by this kind of pervasive and important statistical artifact. And if we need to make some more complex assumptions so that errors might be correlated, or that there might be some more complex measurement models underlying our variables, we can think about how might we incorporate more sophisticated corrections based on structural equation modeling into this broader process. But I think that thinking about what are the potential impacts of the translation between our variables of interest into the measures we actually observed, that's a really critical part of the systematic review and evidence synthesis and critique process that can be really facilitated by estimating adjusted and unadjusted models and comparing the results. The second major artifact that is pervasive in studies across all sorts of disciplines are selection biases. And these occur when the effect size is computed within a sample that does not reflect the population to which we want to generalize it. And it's generally going to be due to selection or conditioning on some variable. So for example, if we are estimating the effect of some phenomenon within college students, that's going to be affected by the college admissions process. And so those groups will tend to be, for example, higher on academic skills, often higher on personality traits that are related to goal striving and goal maintenance, participation in various socioeconomic activities and strata. And so to the degree that we are selecting on these things, that might then induce relationships or attenuate relationships of other variables that are correlated with those. So for example, one of my favorite examples here, actually I'll get to that in a second. So some examples of how selection effects are labeled or described in various literatures, they might include range restriction. If I, for example, estimate the relationship between some factor, some variable, and an outcome of interest, but that factor has been restricted or attenuated in its variability. So for example, if I were looking at the relationship of academic skills with mental health outcomes, and if I look at that amongst college students, then that's going to be attenuated by the fact that that group tends to be higher and less variable than the population as a whole. This also might be called selection bias, or collider bias if they're restricted in some way on some outcome that's creating a spurious relationship. So for example, in our college student example, when students are evaluated by university admissions officers, they will often look at their CVs, their resumes, what sort of activities and grades and things like that do they achieve, before admissions or before application, as well as things like test scores and other indicators of academic skill. In the broader population, there's very little relationship between characteristics related to conscientiousness or dependability or goal striving and academic skill. They're relatively independent or essentially independent. But amongst college students, there is a small to moderate negative relationship between these two variables. And the reason for that is that the way that students tend to be admitted to universities within, at least within the US context, is either by having high academic performance because they've worked very hard and studied and been quite reliable and consistent in their goal striving, as well as them participating in other activities and things like that that are related to goal striving, or by having very high indicators of academic skill. And so by selecting and being able to be high on one or high on the other or both in order to be admitted, that creates and induces this negative relationship between those variables within that selected group. And so if I were, for example, looking at the relationship of these factors with each other, or if I were looking at the relationship with some other outcome of interest, to the degree that I've induced this spurious negative correlation between the variables, that can bias the results of my other variables. So here's an example of that sort of process. So if we look here on the left side, we have direct selection or conditioning on some confounding factor. And if I'm interested, for example, in the relationship between variable z and variable x here, if I were to select and only examine the correlation amongst people who are above the median on z, I might attenuate or reduce the relationship from 0.5 down to only 0.41. So I'm systematically underestimating the relationship of the correlation between my two variables by examining it within a quite restricted subsample. Kind of more seriously, if rather than looking at a direct selection or a direct restriction of range, I've selected on some other factor. So particularly if I'm conditioning on some collider, then I can even change the sign or change, and completely change the relationships. So for example, we might look at panel B here as looking at something like the relationship between our dependability and our academic skills, where overall in our population of interest, those are relatively uncorrelated factors, but then they become seriously negatively correlated once we attenuate or condition on being admitted to a program. And these sorts of selection effects are really ubiquitous. And that's something that we should very carefully interrogate and question as we are looking at as we look at the relationship amongst variables in meta-analyses. Think about how might the sampling factors, contributing to our studies be biasing or especially colliding on our observed relationships and our observed effect sizes. And these factors, selection biases have impacts very similar to measurement error on all three major results in meta-analysis. And there's a wide variety of adjustments based on what different types of plausible selection mechanisms might be underlying our variables or our samples in our studies. And we can use estimates of how has the standard deviation been restricted or limited in our current sample compared to our target or reference population to be able to estimate what might the impact on the sign and magnitude of our effect sizes be if we were to look at it in that broader population. So specific corrections are described in detail in our paper, but broadly we can apply corrections for a variety of different selection mechanisms and measurement error mechanisms using the psych meta package in R with the correct R and correct D functions for correcting correlations and and standardized mean differences. And so we might say, what is the selection model or the correction model we want to apply? So for example, here is correcting for collider bias and measurement error in both of our variables. We can supply our estimates of the reliabilities and range restriction or standard deviation ratios for our various variables. And it'll report back to us corrected effect sizes as well as then corrected standard errors. And we can then use those data, use those approaches as inputs to a meta-analysis, estimated using either the psych-meta package functions, or we can also combine them with the wide variety of methods that are available in the metaphor package and the kind of broader R meta-analysis ecosystem. And so overall, my argument I would like to kind of present to you is that measurement error and selection effects, these are really pervasive, and they kind of plague every single study that we're ever investigating. And considering and applying statistical corrections for these artifacts can help us to give some discipline to our critique of studies and really help to inform our discussions of risk of bias and our critical evaluations of the results of studies, and really kind of make better conclusions, draw better conclusions about what the impact and implications of those studies are for our research questions and our policy and decision making. Right. So thank you again for your time, and I'm happy to answer questions.
Thanks very much, Brenton. And we have some time for questions now, so feel free to add your questions to the chat in Zoom, or you're welcome to also raise your hand, and we'll let our speaker just some moderator call on people if you want to convey your question orally.
Mega, I'm going to read the questions out loud. There's one question by me on the chat. Primary study. Would coders have to be very good critiques of the study to know these errors exist in primary studies?
So basically, the question is, what information do we need to be able to estimate the size of these artifacts? Often, many studies report some estimates that are needed to estimate these. So to quantify measurement error, we need some reliable, good estimate of the reliability of the measure. Many studies will report estimates of reliability, or that is also something that could be incorporated into the meta-analysis process to conduct a small reliability study and estimate, how reliable are these measures. Often, if kind of common or some measures are widely used in a literature, there very often will be measurement and reliability and validity studies available for those. For selection biases, there's a wide variety of different ways that selection effects could be affecting our results, but many of them we can approximate adjustment for them by looking at the ratio of the standard deviation in our our current study sample and the standard deviation in the kind of broader population of interest. So for example, we might have an estimate of the standard deviation of income in our current sample, and then the standard deviation in the broader population that we could pull from, say, a census or labor market survey. Or if we're looking at a particular instrument or scale, we might look at their test norms or their development sample standard deviations, compare that to the standard deviations in our current sample. Largely, I think that these sorts of effect sizes or rather artifact estimates, they aren't kind of much more difficult to identify and extract from studies than are the effect size information that coders are already extracting in order to compute the main focal effect sizes for studies.
Kind of related question is that I guess one of the sense I have of one of the critiques of corrections for measurement error or selection is that oftentimes the data available to estimate the correction factors is itself subject to sampling error. Mm-hmm. And so can you say anything about
yeah,
how to weigh that?
Yeah, absolutely. And that problem, that kind of sampling errors, these things are subject to sampling error, is particularly a problem if you're looking at the bivariate indirect range restriction correction, where it can have pretty severe adverse effects if you kind of treat those artifacts naively and just take them at face value.
Yeah.
And so, the best approach there is to kind of first do conduct meta-analysis on those artifacts themselves. So meta-analyze the reliability coefficients, meta-analyze the standard deviation ratios, and then use the BLUPs, the best linear unbiased predictions of those artifacts in the correction. Or alternatively, if you're using the artifact distribution post-hoc correction approach to extract that variance, the estimated sampling error variance from the artifacts before subtracting those out. And both of those approaches are what's implemented in the SciMeta package to try to yield the most accurate and reliable results of those corrections.
Okay, interesting. And can you say anything about I totally agree with you that these artifacts are really common in a lot of syntheses of correlations, as well as syntheses of intervention effects in psychology, other places that use continuous outcomes. Can you say anything about their combination? So, a lot of the studies that I see in syntheses that I review, that are quite likely to have selection issues as well as unreliability issues.
Yeah. So the selection effects also kind of pull and drag the reliability values around. So for example, if we have some pretty substantial selection effects, that will tend to decrease the reliability of our measures. And so when a selection effect correction is being applied, that correction will lead to an adjustment both in the reliability values as well as in the focal effect sizes. And so, when I, for example, am talking about say a correction for direct range restriction on one of our predictors, if we kind of directly sampled just say the highest scores on our measure, then that correction incorporates consideration of its impact on both the reliabilities and the correlations amongst our measures.
There's another question on the chat by Mohammed Irfan Malik, and we might need some clarification on that. I'm working on meta-analysis on subacute ruminal acidosis. I want to add a moderator analysis for meta-analysis. For example, a study has rumen pH 5.6 and 6.5 for SARA and control, respectively. If I want to add a moderator for NFC starch, the problem is both treatments have different NFC. How do I handle this problem in meta-analysis?
I'm not exactly, without kind of knowing some more context as to what the variables here, it's a bit hard for me to be able to give a good answer. Broadly, if there's kind of concern about differences across the control groups in some of these confounding factors or measurement factors, we might then estimate kind of what is the relationship between group membership and our variables of interest that are affecting our measurement quality. You can feel free to send me an email, and I'd be happy to discuss the particular context here with you.
Another question, if we have time for it, by Jay Jeffries. A brief aside question: is the code for plotting regression lines onto your funnel plot available in SciMeta package?
Yep, that's in the plot funnel package, or the plot funnel function. At least I think it is. If it's not, let me know. There's a bit of a backlog on some feature implementation. Otherwise, the code that I definitely used for that is in our online supplement for the AMPS paper. And so if you go to the OSF repository, you can definitely find the code for that, for those regression lines there.
Great. Let's thank our speaker one more time with the the applause feature on Zoom, or feel free to post your picture up. Our next seminar will be on December 17th with the same Zoom link, same login information and everything. We'll have Dr. Suzanne Jack presenting on one-stage meta-analytic structural equation modeling. Thanks very much to everyone that attended, and thanks very much to Dr. Wiernik again for sharing his work.
Thanks for having me. Thanks, everyone.
Let's see.